Bismillahirrahmanirrahim. Good morning, my dear students, followers, and subscribers. I welcome you to this new video, which is on testing normality. Why normality is important, and why do we need to test normality, and how can we test normality? Various statistical methods which are used for the analysis of data make assumptions about normality, and those methods include correlation, regression, independent sample t-test, pair t-test, and analysis of variance, etc. Similarly, central limit theorem also states that when sample size has 100 or more observations, then violation of the normality may not be a major issue. However, for meaningful conclusions, assumption of normality should be followed irrespective of the sample size. So, this means that normality of data is very important. If a continuous data follows normal distribution, then we present this data in mean or average value. Further, this mean value is used to compare between and among the groups to calculate the significance level, that is the p-value, and if our data are not normally distributed, the resultant mean is not a representative value of our data. A wrong selection of the representative value of data set and further calculated significance level using this representative value might give wrong interpretation. That is why, first of all, we test the normality of the data, then we decide whether the mean is applicable as a representative value of the data or not. If applicable, then means are compared using parametric test, otherwise medians are used to compare the groups using non-parametric methods. Coming to the various methods which are used for testing normality of the data, there are a number of methods available to do this. Among those methods, the most popular methods are Shapiro-Wilk test, that is Shapiro-Wilk test for normality, Kolmogrov-Samirnov test for normality, skewness, kurtosis, histogram, box plot, PP plot, QQ plot, and mean with the standard deviation, and so on. There are a large number of methods which are used for normality of data. As I mentioned, the two well-known tests of normality, that is Kolmogrov-Samirnov test and the Shapiro-Wilk test, are most widely used methods to test the normality of data. The Shapiro-Wilk test is more appropriate method for small sample size. In some papers, it says that it is more appropriate for a sample size of up to 50 observations, although it can handle large sample of size up to 2000, while Kolmogrov-Samirnov test is used for sample size greater than 2000. For both these tests, null hypothesis states that the data are taken from normally distributed population, and when the p-value is above 5%, null hypothesis is accepted, and we conclude that the data follows normal distribution, or the data set is normally distributed. Skewness sometimes is also is used, and it is a measure of symmetry, or more precisely the lack of symmetry of the normal distribution. Similarly, kurtosis is a measure of peakedness of a distribution. The original kurtosis value is known as kurtosis proper. A distribution or a data set is symmetric if it looks the same to the left and right of the center point. that is, it is a bell-shaped distribution, and it is also known as symmetric. If mean, median and mode of a distribution coincide, then it is called a symmetric distribution. Symmetric distribution is also known as a normal distribution, and in that case the values of skewness and kurtosis are equal to 0. A distribution is called approximately normal if the skewness and kurtosis of the data ranges between -1 and +1. That is, if the value of the skewness and kurtosis are somewhere between -1 and +1, then the data set is approximately normally distributed. Although this is a less reliable method in the small to moderate sample size because it cannot adjust the standard error. In order to do that, we will use stata and some data set to show how we can test normality of the data. So let me go to stata, and I have already opened my file here. This is a stata file. So first of all, I am going to use a hypothetical data, and I will ask stata to generate me two variables. So first of all, let me clear the file. So what I will do, I'll ask stata to generate 200 observations. So stata generated 200 observations. Now I ask stata to generate a variable x which is normally distributed with mean 100 and standard deviation 10. So it's here. So this command generated x variable which has the mean value of 100 and standard deviation 10. Let me see. So I ask sum x and detail. So here is the detail of the x variable. So mean is 99.87, so it is almost 100, and this is 9.4, so we can say that this is about 10. The standard deviation is about 10. After this, I would like to generate another variable y, and I write runiform and observation from 20 to 160. So this time I am asking stata to generate another variable y randomly, and the observations, the values range between 50 and 160, and both values are inclusive. So I have generated two values. Let me just check. So these are the values that have been generated by stata. You can see this is these are the x values and these are the y values. Previously those values were not here, are just generated. So after this, I would like to check the histogram of x with the normal density plot. So histogram X, and this is the histogram of x values with normality plot, and the eyeball guess shows that the x variable is normally distributed, and we can also check its normality later on using the Shapiro-Wilk test. Similarly, I can also show the histogram of y with normality plot, and here it is. Now if you look at this value at this plot, Now this data doesn't seem to be normally distributed because you see these bars are not normally distributed. So this is just visual guess or visual examination. After this we will use formalities to see whether these variables x and y are normally distributed or not. So after this, what I will do, I will use a Shapiro-Wilk test. So first I see I apply Shapiro-Wilk test for x variable, and here are the results. This is the value of the Shapiro-Wilk W value, which is 0.99, and its p value is 0.63. So this is greater than 0.05. So we conclude that we fail to reject the null hypothesis, and the null hypothesis is that x follows normal distribution. So the histogram with normal density plot also showed that it was normally distributed, and specifically this Shapiro-Wilk test also showed that we failed to reject the null hypothesis. So this variable is normally distributed. Now we can also do the same for y, and as I told you a while ago that the histogram with normality density plot of y didn't look like a normal distribution. Now we formally use Shapiro-Wilk test for y, and here is the result of the Shapiro-Wilk test. Now this time the p value is less than 0.05, and we strongly reject the null hypothesis, and we conclude that the y variable is not normally distributed. We can also jointly test the normality of x and y by this command SWilk xy, and again the results are here in one. So x is normally distributed, but y is not normally distributed. Now I may also use Kolmogrov-Samirnov test for x or y. X is normally distributed, so I don't apply it to x. I just want to use Kolmogrov-Samirnov test for y variable. And in Kolmogrov-Samirnov test, we use the mean and the standard deviation values of the variable. So first of all, I will check the summary of y with detail. So we will use this mean value and the standard deviation in the formula, and the formula is like this. The command is K-Smirnov of y variable, and that is equal to normal within parentheses y value minus its mean value, and divided by its standard deviation. So it says that the y value is not normally distributed. So let me also check y by another method, and there is a command in Stata, and that is ladder y. And if I give this command ladder y, then it tells us that which functional form of the variable we may use to make this data normal. Now for that, the criteria is that we will compare the chi-square value, and wherever the chi-square value is less, we will use that. So if in the model in square of identity y, that is the actual y values, we use the square root of y, but I think this is the minimum value, this one is the minimum value, log. So if you take the log, then the chi-square value is minimum, and that may normalize the data. So we can do that by generating. So that is how to generate the inverse of y or the log of y. So then we can see the histogram and normality. Let me clear this, and let me use the data from the system. So here is my data, and in this data I have a number of variables. There is one variable which is MPG, and that means miles per gallon. This is auto data. So I am basically interested in testing whether this variable follows normal distribution or not. So I am using the Shapiro-Wilk test for MPG, and here is the test output. The p-value is less than 0.05, so we reject the null hypothesis and we conclude that the data follows normal distribution. After this, I am using this command ladder MPG, and ladder MPG me gives this output. So I will select that form of the variable MPG where the chi-square value is minimum. So I think it's here 0.20, and that is that I will use this form of the y value, that is 1 divided by square root of MPG. So I'll use this one. So first of all, I see the histogram of the MPG in original, and you see the visual examination of this histogram with normal density plot shows that the data of the miles per gallon is not normally distributed. I may also use JB test for MPG, but usually remember JP test is only used for testing normality of the error term or the residual. But let me just for the sake of comparison use the Jarque-Berra test for testing normality of MPG, and this test also shows that this value is far less than 0.05. So the data of MPG is not normally distribution. So let me use this data. I generate inverse square root, that is 1 divided by square root of MPG according to this formula. So if I do this, I generated another variable which is the inverse of the square root of MPG, and now I will check the histogram of this new generated variable with normal density plot. And now if you can see, when I reshaped this variable in another way and I took 1 divided by square root of MPG instead of MPG, now the data look like normally distributed data. And this is the visual examination or the eyeball guess. Now I can use Shapiro-Wilk test for this newly generated variable, which is inverse square root. So inverse square root basically means 1 divided by the square root of MPG. So this is the result of the transformed variable in which I generated a new variable inverse square root that is equal to 1 divided by square root of MPG, and now I applied Shapiro-Wilk test to this new variable. Now the p-value is 0.99, that's much higher than 0.05. Now we fail to reject the null hypothesis that this data follow normal distribution. So in original MPG, when I used the original MPG, the data was not normally distributed, but when I transformed it from identity, that is from the original values, to 1 divided by square root of MPG, now this data became normally distributed. So ladies and gentlemen, in this presentation you saw that we tried to show why normality is important, what are the various tests for testing normality, and we used some hypothetical data by generating x and y, where x was normally distributed and y was not normally distributed. Similarly, then we used some example data set from Stata Auto2 data file, and in that I took the example of MPG and when I applied Shapiro-Wilk test and Jarque-Berra test and histogram with normal density plot, then MPG was not normally distributed. Then I used one command ladder, and ladder advised us to use a transformed variable instead of MPG, 1 divided by square root of MPG. And then when I reapplied Shapiro-Wilk test and Jarque-Berra test, then it showed that the data is normally distributed, and we also guessed it visually by using the histogram and normal density plot of 1 divided by square root of MPG, and that transformed not normally distributed data into normally distributed data. Ladies and gentlemen, I hope this was quite helpful for you. If you like it, kindly subscribe the channel and do not forget to click on the bell icon. And I thank you for watching this video. I would like you to kindly subscribe to the channel and share this channel and various videos of this channel in various WhatsApp groups so that it could reach to maximum possible number of people. Thank you, and see you in another video.